Infinite series. An infinite series is the sum of an infinite sequence of numbers. And we use sigma notation to express an infinite series as we want to sum from 1 to infinity of a sub n, and that means a sub 1 plus a sub 2 plus a sub 3 on out to infinity. And just as we discussed convergence and divergence of sequences, we can do the same for series. The series test for divergence. A series will diverge if the limit as n approaches infinity of the a sub n's are not equal to 0, or if that limit doesn't exist. That is, the limit can be equal to a half, 2/3, -1/5, just something that's not 0, or if it's equal to infinity, then we know that the series diverges. But if we know that the series does converge, this would mean that the limit as n approaches infinity of the a sub n's would have to go to 0. A special type of series is called the geometric series, and it's one that can be expressed as follows. We want the sum from n equals 1 to infinity of a times r to the n minus 1. A is the first term in the series, and r is called the common ratio. In a geometric series, the common ratio is the value for which you multiply one term by to get to the next, and that ratio can be positive or negative. If the absolute value of r is less than 1, then a geometric series will converge, and it converges to a divided by 1 minus r. If the absolute value of r is greater than or equal to 1, then a geometric series diverges. We'll look at some examples. I'm asked to determine whether that series converges or diverges, and if it does converge, I'm asked to give its sum. Well, I'll first apply the test for divergence. That is, check to see if the limit as n approaches infinity of n plus 1 divided by 3n is not 0. Applying L'Hopital's rule, I see that in fact that limit is equal to 1/3. 1/3 is different from 0. Therefore, this series diverges. Example 2, I'm asked to do the same. Look at the series and determine whether it converges or diverges. If it converges, then I'm to give its sum. I'll write out the first three terms of the series, -1/4 plus 1/16 minus 1/64, to see that this series is geometric with common ratio -1/4. That is, to go from the first term to the second term, I multiply by -1/4. Then to go from the second to the third, I again multiply by -1/4. So I know that my series is geometric, and I know the ratio. Well, for a geometric series, we know that they converge if the absolute value of the ratio is less than 1. Well, the absolute value of -1/4 is 1/4, and 1/4 is less than 1, which means that this series converges. And I know that for geometric series, if it converges to a, the first term, divided by 1 minus r, the ratio. The first term in my series is -1/4, so I have -1/4 divided by 1 minus, and the ratio is -1/4. When I reduce that fraction, I get -1/5. Therefore, this geometric series converges to -1/5. In this example, I'm asked to determine the interval for which this series converges and then find its sum. Well, I'll start by writing out the first three terms of the series. I'll have x minus 10 to the 0 power, plus x minus 10 to the first power, plus x minus 10 to the second power, and so on. I see that this series is geometric, with the first term, a1, being equal to x minus 10 to the 0, while any number to the 0 power is just 1, and r being equal to x minus 10. That is, to get from one term to the next, I multiply by x minus 10. I can get from x minus 10 to the 0 to x minus 10 to the first by multiplying by x minus 10. I go from x minus 10 to the first to x minus 10 to the second, again by multiplying by x minus 10. Geometric series converge when the absolute value of the ratio is less than 1. Well, r, the ratio in this example, is x minus 10, so I know that this series will converge when the absolute value of x minus 10 is less than 1. Solving that inequality, if the absolute value of x minus 10 is less than 1, that means x minus 10 is sandwiched between -1 and +1, or that x is between 9 and 11. So this series will converge for values of x between 9 and 11. And the sum of geometric series is equal to a divided by 1 minus r. A was the first term. The first term in this series was 1, divided by 1 minus the ratio x minus 10, and all that simplifies to 1 divided by 11 minus x. In my final example, I'm asked to express the repeating decimal 0.151515 repeating as the ratio of two integers. Well, I'll first observe that repeating decimal can be rewritten as 15 hundredths, 15 10,000ths, 15 millionths, and so on. That is 15 over 100 plus 15 over 10,000 plus 15 over 1 million, and so on. Well, that's the same as 15 over 100 plus 15 over 100 squared plus 15 over 100 cubed, and so on. So this too is a geometric series with the first term equal to 15 over 100 and the ratio r equal to 1 over 100. To get from one term to the next, I multiply by 1 over 100. Because the absolute value of 1 over 100 is less than 1, I know that this series converges. And geometric series converge to a divided by 1 minus r. Well, a was 15 over 100, and 1 minus r was 1 over 100. When I reduce, I have 15 over 100 divided by 99 over 100, which is the same as 15 over 99, or 5 over 33 in simplest form. And if we plug 5 over 33 in the calculator, we see that we do indeed get 0.15 repeating. Thus, the repeating decimal, 0.15, is equal to 5 divided by 33.